Hello, welcome to this video where I'm going to show you how you can build a media mix model and calibrate it using ROAS priors in Stan. This is going to be based on a paper from Google that came out last year. The model is hierarchical, so instead of just having one media parameter and one control parameter, there will be one for every geo, as in geographical location, for example, a state within a country, and then those ladder up to a national level model. And we're going to use 100 geos and do this across 2 years worth of data. Before we fit the model, we're first going to simulate the data using some fixed parameters. Then when we fit the model, we're going to try to get back those same parameters that we use to generate the data. Finally, we're going to fit an uncalibrated geo-level hierarchical media mix model and compare the posterior densities of that model with the one that is used to get more robust estimates using those ROAS priors. All right, let's do it. We are going to follow the simulation in the paper from Google, media mix model calibration with Bayesian priors. In a previous paper from Google, they show how to create a geo-level Bayesian hierarchical media mix model, and that is going to be the basis for the model that they show here. So here you can see what that equation looks like. Now down here you can see in the blue what the posterior ROAS density was from the previous model, which we're going to do today. And then we're also going to calibrate the model using ROAS priors, which is this orange posterior here. And we're just going to ignore this green one today because that's using ROAS for a particular time period during the modeling window. The simulation details can be found on page 11 here at the bottom. It shows how to generate these variables from distributions randomly and then use that to calculate X, which is the spend. And then after that is done, the sales can be simulated using this equation here, and these are the parameters that they use in the distribution functions shown here. And then again, these parameters, tau, beta, gamma, those are generated randomly following these distributions. In addition to this video, there's also a post that you can reference on Medium, which I created. So feel free to check that out if you're lost. For this tutorial, we're going to be using RStudio. So if you don't have that installed, you can go to the GitHub link for this repo, and I will link to how you can install RStudio and things like that. So to get started, first make sure you install these packages. You can just type install.packages and then whatever you want. Just kidding. Okay, we're just going to skip it because it's already installed. Okay. So here we have the number of weeks we're going to simulate, which is 2 years, and the number of geos, which is 100. So you can think of weeks as the rows in a data frame, geos as the columns. And so first of all, as we saw in that equation and simulation, we have to simulate the white noise. So we do it using this random normal function, and we're going to do it for every week and every geo, and yeah, it's going to be a matrix. So there's that. And then the control variable is simulated using a periodic function. So this t is a vector and w is a matrix, and so there's going to be, the vector is going to be broadcast across the matrix. So that'll give us our control variable z. And then we also need to simulate these variables u and rho. So that's what that is. And then this v variable is needed for this equation down here, which simulates the spend. So that's that. And then we're only going to take the positive part of x because we can't have negative spend, so we're just going to do that. All right, so let's run this. Okay, and now we can see what this all looks like. So this is a plot of just one of the geos here, so the first geo, that is, and you can see it's a periodic function with this random noise. And then based on that, we simulated the spend and then only took the positive spend. So that's why what you can see here, and you can see how it's flat in these places because spend there is 0. Next, we need to define the saturation or hill function and the add stock function. So the hill function, I'll just step over here. The hill function is meant to simulate the idea of ad fatigue. So a person might see 3 ads and then they're ready to buy. But if they see 100 ads, it's not going to make them more ready to buy. It'll have this diminishing returns effect. So that's why here you can see the original spend on the x-axis and the transformed spend on the y-axis. So we use this hill function here, but you can use any kind of, well, maybe not any kind, but there are other squashing type functions such as this that you can use. And this one, when the kappa or k term is 1 or less, you're going to see this like C-shaped curve, and then when it's when the slope is less than or equal to 1, you'll see this kind of C-shaped curve, but when it's greater than 1, that's when you have kind of this S-like curve. You can think of it as if, say for this purple line, if you're only spending, say, $1 for a given week, this is going to be how effective it is. But if you're spending $2, it's going to be like this effective, but if you're spending 10, it's not going to be that much more effective than it would be if you were spending 6. So that's the idea behind the hill function. Next, we have the add stock function, which is meant to simulate the carryover effect. So this week, not only are your sales impacted by, not only are they impacted by spend this week, but also previous weeks. So this function in particular is a geometric decay. That is, you can see down when say for the given week, X7, you take the current spend, and then you also add to it 50% of last week's spend, 25% of 2 weeks ago, and then 12.5% of 3 weeks ago. So that's what this function is doing. And so we'll run that quick. The paper also defines that the kappa, slope, alpha, and this L parameter, which is the look back window that we want, those are all defined in the paper. And yeah, so the look back window just means how far back in time you want to use spend for the current given week. I think in one of Google's paper they said if it's 13 or more, it's basically the same as if it were infinite. So after 13 you stop really seeing a change, is my understanding. But anyway, it says to use 3, so we'll use 3. Okay. Okay, then down here we implement the hill function. So we're going to use kappa and slope of 1 each, and then this ROAS spend. And remember, this is a matrix. So we get X saturated, and then we pass it to the add stock function. So it's going to be saturated and add stock. So let's do that. And looks like this was already run. So you can see now that the spend, instead of being at a larger magnitude, it's between 0 and 1. And then if after the add stocking, you can see how here there's where it was previously 0 up here. See, it's flat. It now has a little curve to it, and that's because of the add stock carryover effect. So it's not 0 anymore, it's carrying over previous spend. Okay, and next we are going to choose the parameters needed for those distributions that we saw earlier, tau, k, beta, etc. Each of these is a scalar, and then we're going to sample from the distributions here. These are all just going to be vectors. I forgot to mention we are only going to be modeling for one media channel and one control variable. So that means that this beta is just going to be a number, or it's going to be the number of geos. But if we wanted to do it for multiple beta values, then we would have like beta 1, beta 2, beta 3. But we're just doing it with a single beta, but across all geos because it's hierarchical model. And then down here, epsilon, that's the error, is a matrix. Okay, now we're going to generate the sales data. And like I said, that's on page 12 of the Google paper, and we're going to follow it. It's right here. And so after we execute this code over on the right here, we'll be able to plot the data, which looks like this. We have the sales, and the spend, you can see, is still flat when it's 0. It doesn't go below 0. And then the control variable is going up and down like this in a periodic manner. Next, we are going to calculate the ROAS for this particular media channel. And it is basically going to be the incremental revenue divided by the spend. So C here is the spend, and across all the geos, and across, we're going to say all time. So you could also calculate it for different windows of time, but we're just going to say T0 is week 1, T1 is week 104. And then up here, the beta times the hill function of the add stock function of the spend. That's basically going to give us our incremental revenue. And then we're subtracting it from the same periods of time, but with the spend switched off. So basically this X will be 0, so we can just ignore this last part. And we're going to sum it across all the geos and across all the time, so it's going to give us a full window average ROAS value for these 104 weeks. So here it is in code over here. Just apply the add stock function as we saw, and the hill function, and then do the rest of the equation here, and this, we get this 1.56 as the full window ROAS that we're going to try to get back when we model. Okay, before we can do the modeling, we need to create a prior for the ROAS. And to do that, the paper tells us to do that same data simulation 100 times, calculate 100 ROAS values, and then get the log mean and log standard deviation in order to set the prior. So that's what this graph here is. You can see the counts, the y-axis, and it's of ROAS. And then this is what the mean and standard deviation of a log normal distribution give, the red line. So we're going to simulate it. Might take a while. Let's see if it worked. Okay, it looks like we got 100 values. We have to put this little statement in here in the event that all of the spend that we simulate is negative. Then after we take the maximum of the spend or 0, it's all just going to be 0. So we don't want that. So that's why if that happens, we just skip this step. And as well as down here, and then go to the next one. And then for that given simulation, we would just have a ROAS of 0. Okay. I guess I shouldn't say that because, well, you'll see. So right here is where we calculate the mean, log, and standard deviation. And we have to filter out when it's 0. Okay, so there is the output. And if you want, we could also do this and see what it looks like as a density plot instead. So something like that. And yours might look different if you use a different random seed. Before we can fit the model, we need to reparameterize the linear model equation in terms of ROAS. So right here we have the linear model, but it's still in the form without a ROAS term. What we need is to replace this beta term with something that uses ROAS. So right down here you have the definition of ROAS, which is the incremental revenue divided by the spend for a given media variable. And you can think of this F as just the add stock and hill function combined, as we saw previously, like right here. Okay, and this is going to be summed up across the full modeling window, T0 to T1, as well as all 100 geos. So the first step, and this is really where the innovative part of this paper comes into play, is reparameterizing beta first like this. So originally we have a beta for every media variable and every geo, but now we're gonna just get this beta of the population level media plus these other new parameters where this Z is distributed normally like this. Okay, so then when we do that, we can rewrite the equation like this. So that's by isolating the beta on one side, and that's how we get this equation. And down here it's in terms of now ROAS, this Greek letter KS alpha Z. Okay, and so they stick this in right here. Yep, this H function, and then plus the rest of the equation, like the intercept and then the control variable. So here it is implemented in Stan. We just have the sum of this raw spend times ROAS. ROAS is a scalar, raw spend is matrix, subtracted from eta, that Greek letter, times the sum of this matrix vector multiplication. And then all of that is divided by the sum of the add stocked and saturated media. And then we write this equation as this. So we take beta from up here, stick it down here. And all of these are just scalars because we're iterating through every geo and every week. I want to briefly talk about what makes a model hierarchical. So in a, say, national level media mix model, it looks like this. So there's no geo subscripts, and for sales, you just have one piece of data for every week. So because of that, you also you only have one beta and one control for each media channel or each control. You don't have that structure where within each geo you have its own sales and therefore its own beta, its own gamma control and media parameters. So we can see that here in a hierarchical model. Think of these this middle row of thetas as the geos. So in our model we have 100. Here there are 3. All of these geos come from this population level parameter distribution. And then, like we just said, each geo will have its own target variable or sales, like down here with the Y's. And basically one of the advantages of a geo-hierarchical model is that it is able to use more data. So instead of just, say, 100 data points for 100 weeks, if you also have 100 geos, that's 100 times 100. Now you have 10,000 data points, which is way better for estimating a model. And another advantage is that each of the each geo's parameter as well as the population level parameter is able, say for example, the each state as opposed to the entire country is able to learn from the data of other states. And so each state is connected with one another via the population level parameter. We'll see more about that in a second. So now what I'd like to do is to walk through the Rstan model. At the top we have the hill function and the functions block. It's basically what we've already seen. Then we have our input data, like the number of rows or weeks, the number of geos, which is 100, the spend is matrix, and then the control, revenue, and this L. We're going to assume that it's 3, just like the paper tells us to. And then down here are all the parameters we want to estimate. And so we have the geo level intercepts, the geo level control variables, the sigma term for the error, and the alpha value. We're just going to have one alpha, one kappa, one slope. These are like the hill and add stock function parameters. We're just assuming they're the same for all geos. We have one ROAS as we calculated before. There's one eta that's needed for the reparameterization, and the new z is a vector of length geos, or 100. And then down here we have the population level intercept and standard deviation, as well as for the control variable. And then down here we implement the add stock function. It's a little bit different from what we saw previously, but it's basically the same idea. And then up here we need some of these other variables for the add stock function, so we put them up here and initialize beta to 0, and mu is going to be our geo level, geo and weekly level mean. Okay, and then down here we can see the reparameterization that we already saw as well. Now I'd like to briefly discuss setting up the priors. On the left here we have a Google paper, media mix models with carryover and shape effects, which the paper that we are using references. So a lot of the priors we define are taken from here, but some of them are also given in the paper that we are following. So first we design the population level priors, and we're just again following what it says in these papers. So we have the population level intercept. Instead of from mean 0, standard deviation 5, we're going to make it 10 so that it can capture, better capture the mean intercept population, which is 10. And the standard deviation, like this, as defined in the paper. Same with the control, that also has population level mean and standard deviation. And then down here, the ROAS value is defined using the numbers we got from the simulation. And then, yeah, eta is just a single number, and same with sigma. Or they're being sampled from these priors, that is. And then we have the hill and add stock parameters. And over here we can see this is Desmos. It's a graphing calculator. I'll leave a link to this but basically you can define your own functions and then graph them here. So down here, this is the gamma function, which 3 to 1. So we're saying that, or not 3 to 1, with parameters 3 and 1, it creates a distribution like this that we sample from. And so you could change these around and it would change what the distribution looks like. So you can get an idea of what is happening. It's a pretty handy tool. Okay, we make kappa the same so that it can also take on values similar to this distribution. And then alpha is a beta distribution. So if you remember, that's 0.5 in our model or simulated data. So it's going to be somewhere in here from 0 to 1. And then down here is where we define our geo level priors. So we have, like, every geo has an intercept, every geo has a control variable, every geo has this reparameterized beta variable called z. And this is what makes the model hierarchical. So each of these are sampled from another distribution at the population level. So we define the population level priors up here, and then we are able to define the geo level priors based on the population level priors. And then down here we just define the final model. Remember, mu is coming from up here where we define the linear model, and then sigma is just the error term. I forgot to briefly mention the ROAS prior distribution. So this red is a normal distribution, and so as you can see, it's not very informative. The whatever, say the ROAS could be anywhere from 0 to technically infinity, but anywhere from 0 to 6. But then if by taking our log normal distribution that we calculated, we can define a more informative prior where the true value lies. So that's just to say that setting priors is a powerful way to add knowledge, in this case ROAS, and make your estimates closer to what you would expect. And a lot of times if you fit a model and the priors are not very informative, or the model is not very representative enough of reality, then you'll get a lot of divergences and the model won't converge during sampling. So setting priors is an important part of creating a Bayesian model. Now we are ready to fit the stand model. So here we are setting the cores, then we're reading in the model that we just defined, and then we are running a Markov chain Monte Carlo to generate the samples that are an estimate of what the posterior distribution, joint posterior distribution is for all these parameters. We're going to do 3,000 iterations with 4 chains, and set the adapt delta and max tree depth like this to control the step size so that it is more likely to converge. And this part might take some trial and error. Like when I first started, I didn't do 3,000 samples. I didn't set this adapt delta and max tree depth, so I had to adjust them in order to get the model to converge and have fewer divergences. You can see the results of the chains here. After we discard the first 1500 warm-up, samples, this is what we're left with. There's pretty good overlap with all of these parameters. We're just looking at the population level parameters here. If you remember, our ROAS is 1.56, so this is pretty close. You can also see just kind of some statistics here. The R hat is all 1. R hat means is the variance across all the chains divided by the variance of a single chain, and ideally they should be the same. And so here that's what it looks like. So we know the model has found the posterior distribution. You can see the mean over here, which for some of the parameters like ROAS, it's very close. And for others, not as close, like alpha is 0.37, but it was 0.5. Same with cap and slope. They ideally would both be 1, but it's okay. So down here, we can see the samples plotted. As you can see, the ROAS is really close to the mean, as we said. And some of these other parameters, like slope, look pretty good, close to the slope that was used to generate the data. The mean, that is close. Others like gamma and intercept don't look so great, but potentially by tweaking the priors by tweaking the priors, we could get some better results. But since we're mainly after the ROAS here, I think it's pretty good. So now we are going to fit the non-calibrated model using this equation at the top of the paper. Remember, this was the equation that the ROAS priors reparametrization is based off of. So we don't have to change much in the code at all. This is one of the only parts we need to update the linear model so that instead of having the reparameterized beta here in terms of ROAS, we just have the geo level beta parameters. So that's it. We have to slightly change the model. So now we have this geo level beta prior, which comes from this mean and standard deviation of the population level priors, which are defined in this carryover and shape effects paper, I believe. So now that we have fit the base geo-level hierarchical model, we need to calculate the ROAS because that model doesn't have ROAS as a parameter. It just has beta, kappa, slope, and alpha. And using those posterior estimate or posterior samples, we can get an posterior for ROAS. First, we extract the samples from the posterior distribution and assign them to these variables. There are 6,000 samples total. So the ROAS that we calculate, it's from this geo-level Bayesian hierarchical medium mix modeling paper, which we've mentioned previously. The ROAS is going to be a weighted sum of every geo based on the spend. So that's what this line here is, just getting the sum, the total spend across all geos, all weeks, and then in the numerator, it's just going to be a vector, 100 length vector, 1 number for every geo. And then Here we do the calculation for every set of samples. We do the hill function, and then we do the add stock function, and we assume the L parameter, the look back window, is still 3, and then we do the calculation of the ROAS for each geo, and then we get the weighted average for that particular sample. And so we do that 6,000 times, and now we have 6,000 ROAS values. Finally, we plot the posterior density plots from both models. You can see without calibration, it's not too sure where the true ROAS lies, which is this black line, but you can see with the ROAS prior calibration that the model is much more sure that ROAS is here, which it is. And we can see this is similar in Google's paper. If we scroll to the bottom, how it is a similar sort of difference between the two. So as we can see, the model that lets us incorporate ROAS priors is much better at estimating what ROAS is compared with the model that doesn't use the ROAS calibration. If you have any questions, feel free to leave them in the comments, and I'll put a lot of the links and things that I referenced throughout the video in the description. All right, I hope you enjoyed the video. See ya.